Hey there, it's Shannon Magic Myers coming at you live from San Diego, California. Today we'll be talking about continuous probability density functions. So continuous probability density functions have infinitely many x values. So the way in which we find the corresponding probability is by finding the area under the curve of the continuous probability density function, sometimes called continuous probability distribution. So there are many different probability density functions out there. We're going to focus on two of them: the uniform probability density function and the normal probability density function. So uniform distributions are pretty groovy because they're just a rectangle, right? And we all know how to find the area of a rectangle, right? So this distribution allows us to see very cool properties, two very cool properties. One of them is that the area under the curve of a continuous probability distribution is equal to, you remember? Beautiful, 1. Also, the probability that x is between some a and b is cumulative. So sorry, late night typo. And it's reflected by the interval in which the probability is contained, right? So that area that you find is the same as the probability. Isn't that wonderful? Okay, so here we go. 1 over b minus a. How the heck did we get that? Think about it. What is the area of a rectangle? The area of a rectangle is equal to the base times the height. So how would we find the base of this rectangle? Good. B is to the right of A, so we would just find the difference between B and A. And then the height here, how would we find that height? Well, we know that our area under the curve, this happens to be a straight line, but that's okay. You still get an area under a curve. That's not curved, but it's still a function here. All right, so this area, remember, is equal to the overall area of this rectangle has to be 1 for it to be a continuous probability density function. So what we have going on is we would set that area equal to 1. We know the base is what? Beautiful, b minus a, and then we don't know the height, so let's just call that h. So if I multiply both sides by 1 over b minus a, then this b minus a cancels out or divides out to be 1, and we end up with 1 over b minus a is equal to the height. And that's where this one comes from. Cool, cool? All right, so let's go on to our first example. The waiting time for a trolley that leaves every 45 minutes is uniformly distributed between 0 and 45 minutes. So we're asked to find a couple of things: the probability that a person arriving at a random time will wait between 20 and 35 minutes, and then to find the expected waiting time. So let's check it out. So I can just put my 0 here, and I can put my other end point. So A is 0 and B is 45 minutes. And I need to find my height, but I'm going to go ahead and I'm going to split this interval up into 5s. Cool so far? Awesome. So now, if we call this the x-axis, right, what do we need to find? We need to find our y-axis. So what did we learn? We learned that this y-axis, or the height axis, if you will, the height is 1 over b minus a. And remember that 1 over b minus a would just be 1 over 45 minus 0, right? Which is 1 over 45. Cool so far? Is approximately the height. So we'll put that in. I'm going to actually keep it as a fraction. And let's draw our rectangle. So here, when we draw our rectangle, we have that endpoint. We have this constant height measure. And then we have this over here. So we've got the area of our rectangle. Isn't that awesome? So, I mean, this area, we know the overall area of this rectangle has to be 1. Good so far? So, what we need to do is look at the problem. So, we need to find our probability that people are going to wait between 20 and 35 minutes. Well, let's put a random variable in between there so we can solve the problem. And remember that probability is the equivalent of area under the curve of a good continuous density function. So let's check it out. So if I take a look at our specific little rectangle within the rectangle whose area is 1, and I look at 20 and 35, then do you see that, actually let me kind of erase this one, and I don't want you to get confused. So the overall area, right, of this region is equal to 1. But we're interested in this part right here. Groovy? So, well, we all know the area of a rectangle, right? Area is length times width, or base times height. So the rectangle within the rectangle, if you will, is going to be, we'll have a base is equal to 35 minus 20, which is 15. And remember, our height we found to be 1/45. Groovy? So the area, right, so that area is equal to 15 times 1/45, which is 15 goes into itself once and then into 45 3 times. So we get 1/3. So that means that the probability that x is between 20 and 35 is beautiful, 1/3. I love the uniform distribution. Okay, so now let's see what we have going on. So we want to know the expected waiting time. Well, gee, you know, you have this rectangle. So wouldn't the expected waiting time fall in the middle, right? So 50% of that rectangle would be at exactly halfway in between. Do you see that? So here, what we're interested in is the number when the number of minutes achieves the 50% mark, or the 0.5 area, right? Well, we know that our 0.5 area will be when we're exactly halfway at the base, and then this whole region right here would be area equals 0.5. So what we need to find, well, we're talking about time, waiting time, so we need to find the minutes where that will happen, right? Well, in general, the expected value of a uniform distribution is b minus a divided by 2, because that'll get you exactly at the center x value for your distribution. So our b minus a was, beautiful, 45. And when I divide that by 2, I get 22.5. So the expected waiting time is 22.5 minutes. All right, cool so far? Awesome. So now let's get into the standard normal distribution. So the standard normal distribution is a continuous probability density function with the theoretical mean mu equal to 0 and the theoretical standard deviation sigma equal to 1. The total area under this curve is what? Awesome! 1. Okay, so far? So, all right, here is what the equation looks like. Trust me, this isn't as bad as some of them. This is when mu is 0 and sigma is 1, so it simplifies quite a bit. But the cool thing about this distribution, and something that I think is a little lost sometimes, is it goes on infinitely, right? So this would be like your z-axis, because it's the standard normal. And it goes, on infinitely. So if a person was to, if you had some calculus, if a person was to find, the improper integral from minus infinity to infinity of this function, which is typically written as 1 over root 2 pi times e to the negative x squared over 2 with respect to x, this gives you area under a curve. Well, it turns out that this improper integral is equal to 1. It converges to 1. So this is a probability density function, and since it's an axis for z, this is when z is 0, 1 standard deviation above the mean, 2, 3, 4. I mean, you could keep going on. We don't always, but you can just keep going on and on and on, right? And then we've got standard deviations below the mean. And even though it doesn't look like it, there's still a teeny bit of area, right? So it closes out enough to where we end up having this density function. So this total area under the curve is one. And it's cumulative, right? So the overall area, this overall area is equal to 1. And it's cumulative. So each little area that gets added on, or each little probability for each z-score gets added on to the one before. And so this, in most of your charts and stuff like that, they give you the probability that z is less than some value, right? Call it z1. Right, so if z1 say was right here, then we would get this probability, just for the yellow part, would be this probability. Okay? All right, so let's move it along, keep going. If you use a table, what you can do is you can find your area, or remember it's probability, inequalities. Such areas can also be found using a graphing calculator, or a statistical software package like JMP that we've been using, and we'll explore that soon for these functions. When using a table, it's essential to understand these points. So you need to understand this because you will be tested about how you'd use a table, because I believe that will further your understanding in this concept. The table is only designed for the standard normal distribution. And that's that special case that has a mean of 0 and a standard deviation of 1. Our table finds the probability that x is less than or equal to x, or the probability that z is less than or equal to some z-score, which is x minus mu over sigma. So our table representing the standard normal distribution is on 2 pages. Each value in the body of the table is an area, which is also, remember, a probability. The beautiful part of all this is that the area to the left of z represents the probability that z is less than some standardized value. So in other words, your z1. So there's all kinds of z's. So when working with a table, avoid confusion between z-scores and areas, or z-scores and probabilities. The z-score is found along the horizontal scale of the standard normal distribution. So you refer to the first column and first row of our table. Area under the curve to find that, you refer to the values in the body of the table, and you find the corresponding z-score. So just kind of a big picture idea, all right? So this is assuming a standardized value. So we're going to start with the bottom 2. So let's suppose that we have A is here, okay? So the probability that Z is greater than some A would be this area to the right of A, all right? And then if we come over here and we talk about, let's just say that B is over here, all right? And if we look at the probability that Z is less than B, you'd have all this region here. Good so far? Awesome. So now if we want to know the probability that Z is in between these two, I mean, do you see that you'd have your B here, and you'd have all that area, but you would want to subtract out the part that was added too much, right? So you would want to subtract out the area that's less than that marker B, bounded by the start of A. Cool so far? All right. So here we go. Set this one up. This one, whoa, sorry. Would be this area. So the area in between is actually going to be the probability that Z is less than B, which gives us all of that. And then we want to take away what's, been counted too much, that extra area. And the extra area is actually right here, isn't it? Sorry, wrong picture. The extra area is right here. So we would subtract out the probability that Z is less than A, and that gives us the probability that you have a value in between those two. So the probability that Z is greater than A, in our table, what we do is we actually find out the probability. So this is the one shaded in black. We find out the complement. So 1 minus the probability that Z is less than A. And that's going to give us this region here. Cool, cool? Turns out this is also equal to the probability that Z is less than negative A. And then this one's, the same. It's very straightforward. You just view that and you get your area. Okay, so far? Awesome. All right, so let's look at an example. Suppose that the weekly sales at a women's shoe store are normally distributed with a mean of $8,500 and a standard deviation of $650. 1 week is randomly selected. What is the probability that this week's sale total more than $7,500? So what ends up happening is you have like two scales here, right? So you have your mean of 8,500, right? But then you also have like the scale underneath for Z. So this scale is X and the bottom scale is Z. And so this would be 0 because 8,500 is the mean. So it's 0 standard deviations from the mean. Okay, so far? Okay, so we're interested in this value of 7,500, right? So if we ought to standardize, which we have to do if we're using the table, right? Then we need to find this Z1, the X value minus the mean over sigma. So our Z1, the X value is 7,500 minus our mean, which was 8,500, all over sigma, which was 650. Okay, so far? So when you do that calculation, you get a value that Z1 is, let's check it out. I got this app, so hopefully it looks somewhat like your graphing calculator. All right, so we're just doing this computation, 7,500 minus 8,500, and remember to put parentheses around it, and we're dividing it by standard deviation, and we get sorry, this one goes to, for some reason, defaults to fractions, which is usually good. But in this case, we're looking for the decimal. So we get approximately, we want to go to the nearest hundredth, so negative 1.54. And that makes sense, right? Because 7,500 is under the mean, right? So, all right, well, remember this would be the number of standard deviations below the mean. I'm not going to worry about the x1 yet because I'm going to show you that on a different problem, all right? So here we are. The negative 1.54 is going to be, I don't know, about here. So if we take a look at this, this is our boundary value. Okay, so far. So this is our Z1 approximately equal to negative 1.54. Good so far? Awesome. So now let's go back to the language of this problem. We want to find out the probability that this week's sales are more than 7,500, right? So more than 7,500 is all this stuff here. So we got to know that it's going to be more than, beautiful, more than 50% because we have more than half the area that's contained, all right? All right, so that's the probability we are looking for. Good so far? Now, here, remember that we have symmetry, right? So this probability, okay, so the probability that, first of all, x is greater than some x is equivalent to the probability that some z is greater than the z1 that we found. And that would be the probability that z is greater than negative 1.54. Cool so far? All right, but remember there's symmetry here. So you can either do it finding the complement, right? Or we could take a look at this little teeny area here, the opposite of Z1, which would be positive 1.54. Right? And so it would be this region right here. Do you see that this region here, if I find the area to the left of that, right, it would be equivalent, right? So I'm going to do that. I think most people have best luck if they're using symmetry. You can use complement if you'd rather, that's fine. So this is equal to the probability that z is less than the opposite of negative 1.54, which was the probability that z is less than positive 1.54. And now let's check out our table. And this is, you know, the probability that z is less than some standardized score that's less than 0. We are looking at the probability that z is less than 1.54. So what we do is this. Here's the 1.5. That's the first part of the z score. See how it says z? And then the second part is the decimal place for z. So negative positive 1.54, sorry, is going to be over here, and that's from the meetup of these two values. Cool? And this area makes sense, right? It's going to be 0.9382, and that was a very big chunk of area that we had. So 0.9382. Okay, well, you're probably saying, what about the calculator? Blah, 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 right? So here we go. Let's look at how we would use the calculator. We would say you go to second, all right? And then distribution. We press, let me make it bigger. We pressed second and then distribution, which is the second command on vars. Okay, awesome. Okay, so for this one, we selected the normal CDF. Right here. And then it brought us to and this is where we plugged in that value, some real small value. And then we went to our 1.54, enter. And we get our result here. Okay, so far? Awesome. All right. So now what we will do is we're going to take a look that this week's sales are less than 10,000. So again, we're going to want to find a z-score. So the probability that some x is less than 10,000 on a standardized scale is equal to the probability that z is less than some other z, call it z2, right? And let's find z2. So we have z2 is just going to be our x, which is 10,000 minus 8,500 divided by 650. So our z2 is going to be approximately So you can also do this and just hit enter because I forgot the parentheses and then divide it by 650. And then we want to get to the decimal. And we have approximately 2.31. Okay? Sorry, my dogs are going bananas. All right, so this will be equal to the probability that z is less than 2.31, where this one is z and this one is x. You'd have your 8,500 for the mean, and this would be our 0. And then we've got 1 above, 2 above, 3 above, and over here 1 below, 2 below, and 3 standard deviations below. And since we're working with these standardized values, this is what we will do. So we'll have our color, did I do it last time? This one won't be as complicated because it's already a less than. So 2.31. So 2.31 is about here, right? So Z2 is 2.31. And so if I bring that up here, then we're looking at this whole area. Groovy? So again, this should be pretty big, right? Even bigger than the one before. So let's take a look at the table. We just need to look up Groovy 2.31 on the table. So again, we'll go to 2.3 is here, and we got to go to 2.31, so that would be this one here, and that's from this connection here. So this is point what, 9896. So very good probability of having less than $10,000 of sales. Okay? All right, so now, again, if you go to the calculator, you would start out the same, so I'm not going to do all the screenshots. Another cool trick with the calculator is that if you go second entry a few times, see how it keeps taking you back? So again, we're going infinitely to the left, aren't we? And what we want to do is have 2.31 instead. So that's sort of a nice little trick that you can do. And look, we get 0.9895, all right? And here's the end result with the calculator, okay? And again, usually that if there's a small difference, it's due to rounding of the z-scores. Okay, so now let's check out the next problem. What is the probability that this week's sales fall between 7,500 and, oh, whoops, I wanted to relate it to the problems before. So we're going to do between 7,500 and 10,000, all right? So with the putting in the z-scale below, right? So this is our z and this is our x, and again, 8,500 is the mean, and so that's 0 standard deviations away from the mean. And these go above the mean, standard deviations above, standard deviations below. Okay? So what we're looking for this time with those z-scores we got last time and the problem before, right? So the probability that x lies between 7,500 and 10,000 is going to be the equivalent to the probability that z1 is less than z is less than z2. Remember, that's what we had called those values. So remember that we had the z1 was equal to what? Good, negative 1.54, right? We're going to actually be going a different direction from it this time, but that's okay. So less than z, less than, and then z2 was over here, and it was 2.31. Good so far? Awesome. And recall that that is equivalent to, if we look at these regions, so 2.31, that's z2, and negative 1.54 be about here, would be z1, both approximate. So we would have these boundary lines, right? So we're interested in this region here, right? But what we need to do with this is we actually need this little teeny, oh goodness, I'm sorry. We actually need this little teeny region right here to be subtracted out from this overall region here, which would be here. So let me put the green above it. Okay, so let's do it. So this will be equivalent to the probability that z is less than 2.31 minus the probability that z is less than negative 1.54. Okay, so far? Good. So we already found that first probability, and that was equal to 9896 using the table. Now we have to find the other probabilities. If we go to find the other probability, we'd be at negative 1.54 and then 0, negative 1.5 and then 0, 1, 2, 3, 4. So 0.168. So that's the hundredths place. This is the other part of the z-score. So now if we come back there, 0.618. All right, so when we do that computation, we're going to get 78. Double check those areas. Yeah, and then we found the other one from the table. Okay, so that's the probability that the sales fall between 7,500 and 10,000. Cool, cool? All right, so I want to show you something else here. There is another way that you can do these without standardizing, but you got to make sure you know how to standardize, because I may have you do some of this stuff using the table and not using the calculator on the exam. So if you come back here and you do your regular stuff, second distribution, and you go to normal CDF, right, you can actually do the X numbers, but you got to include the mean and standard deviation in this order. And lo and behold, 0.9275, and the difference, rounding of the z-scores. Cool, cool? All right, so now what is the range of weekly sales that would be considered normal? What do you think? What do we have going on here? Well, remember that 650 is the standard deviation, right? And within 2 standard deviations of the mean is considered normal. So if I add 650 to here, I'll get 9150. Another 650 will be 9800. And then another 650 will be 10,450. And then if I go the other way, I'm subtracting 650, so that would take me to 7850 on this end. And then we would have 7,200 and 6,550, right? I just added and subtracted the standard deviation of 650. So if we want to figure out what is normal, what should we do? Well, we would look at this information here, right? This is 2 standard deviations below. This is 2 standard deviations above. We're looking at the X values, right, that correspond. So do you see down here, we can say the range of weekly sales that would be considered normal are between, actually, should probably say sales between 7,200 and 9,800. Cool? All right, so that's the answer to this one here. And let's see what we have here. So we've done quite a bit of work of taking the z-scores and finding the area, but why don't we also look the other way around, right? So remember that when you're looking for area, you look in the body of the table and you find the z-score that corresponds. So our first one is an area of 0.5000. So if we go to our table, do you see that we have, let's see, 0.5000 right here. And that's, unsurprisingly, a z-score of what? 0, right? Because you've got your mean, right? Half should be below, half should be above. So here we go. That would be a z-score of 0.00. All right, so what about 0.25? Let's check it out. So if we go to 0.25, so do you see that 0.25 is going to be in between those two areas, right? So what you do is you go to those corresponding two z-scores, right? And you average them. So if you go and take the average between these two, do you see the average here would be 0.075, right? And then you just add this part of the z-score, so you'd get negative 0.675. All right, cool. Okay, and then what about 0.75? Can you guess? Let's see. So 0.75 is going to be on the other side of the table. And look, that's why I was saying that. Do you see? You're going to have those. You've got the 0.6 because of symmetry, right? You're going to get the same deal, but the opposite sign. So average of these smaller parts is 0.075, and now you have the 0.6. So our result will be positive 0.675, which should be expected because of symmetry, right? Okay, let's look at 0.2345. So again, coming down to the table, 0.2345 would be in between these two, right? Should probably do that in a different color. So in between these two values, and so if we, again, it's at 0.7, and then we go and average these two z-scores, this average would be, between those two would be 0.025, and then the score that was over here was negative 0.7, so we'll get negative 0.725. And you do carry the digits out when you average the z-scores. You carry them out one more than normal. Okay, and then let's take a look at an area of 0.8992. All right, so here, I'll find a different color. We'll do pink. So 0.8992 is going to be on the positive side, 8992. It's going to be between these two, all right? And so we'll have this 1.2, and then we would average these two again. And remember that the average was 0.075. So we'll have 1.275. Okay, so now let's do an example where we use the calculator, because I think that's the last, yes. So using the calculator, this is what we do. So we go to that same deal, the distribution. Now we do inverse normal, okay? And so we were entering in areas, right? And so we have, our area was, one of them was what, 0.2345, right? And we're using standard normal, so let's see if that's what we got for our z-score. Do we get negative 0.72 for 0.2345? Let's check it out. It's 0.2345, and yes, we get negative 0.724 on the calculator, negative 0.725 using the table. So that is how you would do it. All right? And again, this is the one that we looked at. Groovy? Okay, I hope you have a wonderful morning, afternoon, or evening whenever you're watching this, and I'll talk to you soon.